Okay, it's 4 o'clock and we are going to start. The Honorable Director of our Institute, Dr. Sanjay Bihari, the guest in our midst, Dr. Rajagopala Chidambaram, the Dean, Dr. Ajit Kumar, the Deputy Director, Dr. Keshav Das, members of our faculty, students, staff, and other guests. A great day indeed for us at the Sree Tirunal Institute for Medical Science and Technology. As we have a former president of our institute, and more importantly, a doyen amongst our scientific community, Dr. Rajagopala Chidambaram, in our midst to deliver the lecture titled Indian Science and Technology from Raman Effect to Nuclear Power. How do you recall Dr. Chidambaram? As a citizen of our nation, I wish to relate him with pride on the fact that we are part of a society that has harnessed nuclear energy for peaceful purposes in use. Also gives some reassurance as a citizen of a nuclear capable nation, fitting the adage that it is better to have a nuclear weapon and not wanting it, rather than wanting a nuclear weapon and not having it. Sir, we recall your iconic photograph at Pokhran in 1998, donned in the army fatigues of a general, with the then Prime Minister Sree Atal Bihari Vajpayee, Dr. Anil Kakodkar, and the indefatigable Dr. APJ Abdul Kalam. Coming to the topic of the day, we must accept that we need to take stock of our scientific prowess as we stand on the shoulders of giants like Dr. Chidambaram to look further. As a nation, we are proud, not because we have had Nobel laureates, but because of our strides in nuclear energy, space program, supercomputers, medical sciences, etc. Our recent response to COVID-19 disease with mass vaccination is another feather in our cap, a step that has been acknowledged to have reduced deaths and disability. Let us not rest on our laurels, but let us move forward toward the frontiers of science and technology on the difficult roads traveled earlier by our predecessors, including Dr. Chidambaram. Sir, welcome to the second lecture of the Samvaad series. The brainchild of our director, Dr. Sanjay Bihari, meant to showcase Sree Tirunal Institute for Medical Sciences as a platform for discourses on science, medicine, and public health, the three realms where our institute has a significant presence. Let us get the ball rolling here today. I invite Dr. Keshav Das, former Dean, HOD Radiology, and Deputy Director Designate, to introduce our speaker to this august audience. Over to you, sir, Dr. Keshav Das.
Good evening. Dr. Rajagopala Chidambaram became the director of Bhabha Atomic Research Center in 1990. He was chairman Atomic Energy Commission from 1993 to 2000. He was the principal scientific advisor to the Government of India and the chairman of the Scientific Advisory Committee to the Cabinet from 2001 to 2018. He is presently the honorary chairman, School for Advanced Studies in Nuclear Science and Technology in BARC. Dr. Chidambaram has made important contribution to many aspects of our nuclear technology. He has DSc degrees from 30 universities from India and abroad. He has more than 200 research publications in refereed journals, and all his research work has been in India. He was chairman of the Board of Governors of IAEA during 1994 to 95. During 1990 to 99, he was a member of the Executive Committee of the International Union of Crystallography, the last 3 years as its vice president. He has been chairman, Board of Governors of IIT Bombay, IIT Madras, and a member, Space Commission. Dr. Chidambaram is currently chairman of the Board of Governors of IIT Jodhpur and IIT Delhi. Dr. Chidambaram is a fellow of all major science academies in India and also the National Academy of Engineering and the World Academy of Sciences, Trieste, Italy. He was received many awards and honors. Notable among them are the C.V. Raman Birth Centenary Award of the Indian Science Congress Association in 95, the Distinguished Material Scientist of the Year Award of the Material Research Society of India in 96, R.D. Birla Award of the Indian Physics Association in 96, Homi Bhabha Lifetime Achievement Award of the Indian Nuclear Society in 2006, the Lifetime Achievement Award of the Indian National Academy of Sciences in 2009, and the C.V. Raman Medal of the Indian National Science Academy 2013. Lifetime Achievement Award of Andhra Pradesh Academy of Sciences 2014, Lifetime Achievement Award of the Council of Power Utilities. Above all these, Dr. Chidambaram was awarded the Padma Vibhushan, the second highest civilian award in India in 1999. His initiatives as principal scientific advisor to the Government of India include the setting up of the core advisory groups of research and development in various technology sectors, the creation of Rural Technology Action Group centered in 7 IITs, the establishment of Society for Electronic Transactions and Security, helping nucleate the Centers of Excellence in Nanoelectronics, and the National Knowledge Network, and initiating an R&D program on the design of the advanced ultra supercritical thermal plant through a consortium of IGCAR, BHEL, and NTPC, which has now been completed. This is, in short, our Chidambaram sir. Over to you, Dr. Ishwar.
Thank you, Dr. Keshavdas sir, for calling in when Dr. Ajit sir became indisposed today because of a respiratory infection. I invite Dr. Rajagopala Chidambaram to address this gathering here today. Can you please move the camera a little closer? Sir, we are seeing you from a distance.
The camera is already fixed.
No, unfortunately, the camera is fixed. We cannot change it.
All right. Okay, sir.
And I've done it deliberately because it shows BRC behind.
Okay.
I belong to BRC. That's my lifeline. So I've deliberately kept it like that.
Okay.
Dr. Sanjay Bihari, Dr. Ishwar, Dr. Keshavdas, Dr. Ashalata Radhakrishnan, colleagues from SCTIMST, ST, friends. It was not probably mentioned that I've had a long association with Sree Chitra Tirunal Institute. Of course, maybe you mentioned. During the time of MS Valiathan and Dr. K. Radhakrishnan and also little Dr. Asha Kishore. And it is a pleasure to be back with you again and during the Amrit Mahotsav year. And so I thought it will be a good time to kind of look back at our achievements in science and technology. From basic science to high technology. So I chose the topic as Achievements in Indian Science and Technology from Raman effect to nuclear power. Next slide. As you all know, India celebrates 4 days in science and technology. The day C.V. Raman, the greatest experimental physicist India has produced, kind of announced the discovery of the Raman effect, named after him. That's the science day. Birthday of Srinivasa Ramanujan, who has been called a natural and magical genius. Come back to this in a moment. Mathematics Day. The birthday of Mokshagundam Visvesvaraya, the greatest engineer, civil engineer India has produced. Engineers Day. And then now the Technology Day. May 11, the first day of the 1998 Pokhran tests. See, when Raman got the Nobel Prize and was there in Sweden, Stockholm, to receive the Nobel Prize, this is his comment. When the Nobel Award was announced, I saw it as a personal prayer, an achievement for me and my collaborators. But in Stockholm, when I sat in that crowded hall and I saw the sea of Western faces surrounding me, and I, the only Indian in my turban and close coat, it dawned on me that was really representing my people and my country. I felt truly humble at that time. Then I turned around and saw the British Union jack under which I had been sitting. And it was then that I realized that my poor country, India, did not even have a flag of our own. And it was this that triggered off my complete breakdown. You know, Raman was a very tough guy. Well, this is a very rare occasion when when he broke down. Today, 75 years after independence, the young people have huge opportunities. Wonderful institutions have been built up, including your own Sree Chitra Institute, and in fact in every field. So the young people have opportunities to fully bring out their talent and go for great achievements for themselves and for India. Next slide. See, this is a very interesting biography of Chandrasekhar by Kameshwar Wali. And Wali asked Chandrasekhar, how did India produce world-class scientists like Raman and S.N. Bose in 1920s? So Chandrasekhar said in the 1920s, there was a need for self-expression as a part of the national movement. To show the West in their own realm, we were equal to them. And that's what Raman showed, and so many others. And Sommerfeld, the great physicist, who so many students have contributed to quantum mechanics, he has said that India had suddenly emerged in competitive research as an equal partner with their European and American sisters. Today, as I said, 75 years after independence, the motivation should be to make India a developed country and a knowledge economy. Knowledge economy with an ability to produce new knowledge in every scientific field, and also to appropriate knowledge that is generated everywhere else in the world. And this process has already started, both in science and technology. This is what leaders like Homi Jahangir Baba have tried to do in nuclear technology, Vikram Sarabhai in space technology, and so on. Next slide. This is Baba. Now there's a beautiful book by Arthur Koestler who talks of two kinds of leaders, the yogi and the commissar. Yogi is the contemplative thinker, the man of action, and the commissar is the man of action. Baba was a unique mixture of both. You know, all of us tend to be more of one than of the other. Baba, of course, it is arithmetically wrong, was almost 100% yogi and 100% commissar. And you know, there are many leaders, when they disappear from the scene, they leave behind a vacuum. But Baba had created a leadership swarm around him. Raman in physics, Brahma Prakash in metallurgy, Setna in chemical engineering, A.S. Rao, so many others. So that even though he passed away tragically at a young age, 56, in 1966, at the age of 56 years, the atomic energy has continued to flourish. Next slide. Srinivasa Ramanujam I mentioned. A beautiful biography of Srinivasa Ramanujan. But there is one which was really, that's also very nice. The Man Who Knew Infinity. Now, K. Srinivasa Rao has written a new biography. And, you know, it's called a mathematical genius. Mathematical genius. That's what Nobel laureate Chandrasekhar said. As long as people do mathematics, the work of Ramanujan will continue to be appreciated. Next slide. Now there is a talk of robots, artificial intelligence. People even talk of super intelligent robots. Some people are scared that some of the robots won't become so intelligent that may take over from man. I don't believe that. But here, Professor Ezekiel Dror, while reviewing the book on The Man Who Knew Infinity, Ramanujan, he says this is a fascinating book. And of course, everybody knows he was a super genius whose theorems with novel ideas from his handwritten notebooks. He gave the theorem, either the proofs were obvious to him or he didn't bother to write it down. And people have spent generations have spent time, and students have got so many doctorate degrees proving those theorems. Intellectually back-breaking cost. True. Nothing has been proved untrue, really. And leave mathematicians baffled that anyone could divine them in the first place. That's why when talking of these so-called super intelligent robots, Dror says no enhancement of human intelligence opens the door to becoming a Ramanujan. And no algorithm is likely to produce robots with the abilities of Raman. Next slide. Coming back to medicine, of course, as I said, we have produced a great pen in every field. I mentioned some of them. Look at some of the famous doctors of modern India. You know more about it than I do. Kadambini Ganguly, the first female practitioner of Western medicine in India. Pindarnath Brahmachari, the discoverer of urea stibamine. Villapragada Subbarao, who discovered, of course, this work was done abroad, and so on. And next slide. But there's one area in which we are picking up now medical device development in places like BARC, CSIR, DRDO, IIT, and so on. So I'm very happy that Sree Chitra has this BMT wing, biomedical technology wing. Even at the time of Dr. M.S. Valiathan, the Sree Chitra heart valve has been developed. And it's same, as you can see, to undertake research on frontier areas of biomedical science and technology. We must really work to cut down the import of medical devices into the country. Next slide. Look at achievements of modern Indian medicine from a report from the Office of the Director General of Health Services. We have achieved a great deal. Eradication of smallpox, polio, leprosy, yaws, containment of a lot of other diseases, cholera, widely prevalent, brought under control. But there are similar achievements of modern India in every science: agriculture, nuclear, space, defense research, and so on. Next slide. Take agriculture, for instance. There was a time when India was dependent on imported wheat, but with the first generation Green Revolution, M.S. Swaminathan and so many of his colleagues were involved in this. India has become a global agricultural powerhouse, largest producer of milk, pulses, jute, spices, because all this has also an impact on health, world's largest cattle herd, and so on. But still, climate change issues are there, land holdings are fragmented, productivity is low, but then just become compensated by the number of people who work in agriculture. That is why the environmental stability of current agricultural practices in India, because the rapid depletion of groundwater table, soil degradation. But the good thing is people are aware of it and things are being done to correct these kind of situations that you hear. Next. Nuclear in that area we have. And this is the reactors around Kaiga reactors in Karnataka. I wanted to show this slide. You know, we take care of the environment. Every tree that we cut to build a plant, and we have unfortunately to do that, we plant 10 trees. You see the greenery around the Kaiga reactors that you see. Next slide. And India is one of the few countries in the world which has comprehensive capability, the entire fuel cycle. See, from the milling and mining of ores, fuel fabrication, designing nuclear reactors. You know, uranium-238 in the 235 burns in the reactor. 238 gets converted to plutonium-239. Similarly, thorium-232 gets converted to uranium-233. You can reprocess it and make fuel out of this, which are used in fast reactors, like in Kalpakkam. So when, as I said, we have capabilities in almost every field here that is shown here: reprocessing, conditioning, recycling, waste storage. Next slide. See, nuclear is not just nuclear power and nuclear weapons. And as many of you know, in Sree Chitra, applications in practically every field, food preservation. We are able to export Alfonso mangoes to US because if we irradiate it, the shelf life goes up. Then production of so many radioisotopes which are used in medical diagnostics. I've given a few examples here. Cobalt-60 gamma rays for cancer therapy and so on. Next slide. See, India, there is a very interesting book by Nassim Nicholas Taleb, and he talks about anti-fragility. See, there are things, robust things, don't break down under stress, under shocks. Resilient, resist shocks. And fragile breaks down under shock, under stress. Anti-fragile gets better and better. Like some of the antibiotic resistant bacteria, which have their bacterial resistance, as I mentioned. So I've always said our nuclear program is anti-fragile. They try to put us down by technology denials. And when I was Director BARC, I defined self-reliance not as trying to do everything yourself. If something is available to you from a reliable source, don't waste your time. Go ahead and buy it. But if anything is denied to you, including the proverbial wheel, you must have the capability to do it yourself. So my definition of self-reliance was immunity against technology denial. Now that stage is over. Everybody recognizes our strengths in the nuclear field, also space. Today we should leverage international cooperation to strengthen our initiative. And the world realizes that is how, especially they took India out of the NSG, Nuclear Supplier Group guidelines, to prevent supply of materials to India. When they realized we are not a buyer, but we can be a provider, that's what they did. Next slide. See, now one of the biggest threats to the world is from low carbon, from climate change. Warming of the climate, there's no doubt about it. It's unequivocal. The atmosphere, this is the report 2014 confirmed in the 6th report 2022 that warming of the climate system is unequivocal. The atmosphere has gone up, warmed up by about 1 degree during the time from the Industrial Revolution to 2012, gone up further, maybe by half a degree. And people have realized that you cannot allow it to go beyond 2 degrees, preferably block it here. And it is caused by carbon dioxide emissions mainly, for there are other greenhouse gases. You go and settle upstairs, prevent the infrared radiation from going out of the earth, get it reflected back. And that's what causes global warming. And this report says key measures to achieve mitigation goals include development of renewable energy, nuclear, carbon capture and storage, including bioenergy with CO2 capture. I would also add advanced ultra supercritical thermal plant, It's a program which was mentioned in the introduction, which I started when I was the principal scientific advisor. Whatever is say next 20 years, we are going to be burning a lot of coal. But we are able to take the steam to a higher temperature, say above 700 degrees, like what you do in this advanced ultra-supercritical thermal plant. For the same carbon dioxide emission, you are able to produce more power. Now, Stanford University study shows global warming has increased economic equality since the 1960s. Remember, we are in the southern part of the hemisphere. The northern part, which are the cold regions, they say, thank you very much, if it warms so good for us. Norway and Sweden, and their economies have in fact improved, or the Siberian region of Russia. But in the long term, it's going to affect everybody. So now they realize that the short-term advantage is counterproductive. Everybody has to contribute to cut down these greenhouse gas emissions and reduce global warming. Next slide. See, as I said, there is nothing India cannot do. That's my general principle in life, not only in nuclear, I think in general. So when we were asked, in fact, Dr. Raman asked me in 1969, design these devices, and we formed a group and then we designed it. So this is a paper I wrote in 2008 in this international journal, Atoms for Peace. And let me read it because it summarizes the work that we have done. The design of the devices for both the tests, 74 and 98, were the culmination of committed effort in BARC. The only thing we could not do was chemical explosion, because you need chemical explosion lenses to produce the spherical shock wave that we need for implosion. And so we involved, and they did a wonderful job, DRDO lab, the Terminal Ballistics Research Lab in Chandigarh. And then, of course, design of devices is not a single discipline. You need a range of disciplines: explosive ballistics, shockwave physics, condensed matter physics, material science, nuclear and neutron physics, radiation hydrodynamics in the case of thermonuclear device. And also in those devices, you also have to work out the radiation matter interaction physics. And then you must have electronics engineering of a very high caliber control systems. And also the necessary capability, computer simulation software to enable accurate prediction of weapon use. In each one of these areas, we have some of the world's leading experts. So as I quote this sentence from my write-up, the carefully planned series of tests carried out by us give us the capability to design confidently and build nuclear weapons from low yields up to around 200 kilotons. You see, the thermonuclear device we tested was 45 kilotons. Because, you know, we already had a shaft which had been dug. Actually, it had been dug from Rajiv Gandhi's time, and we had to do quickly the test there. What happens in an underground nuclear explosion is, of course, the area, the volume around the nuclear device, the rock gets vaporized, becomes a source of a shock wave. Then the shock wave proceeds in all directions. You know, when a shock wave goes through a material, not only does it compress, but it also heats the material. And as this shock wave goes, because it's no longer high enough pressure, shock pressure, to vaporize the material, it will melt the material. So you now have a situation in which you have a large cavity, several meters in diameter, of hot radioactive gases surrounded by a layer of molten rock. Then it is not strong enough, because a divergent shock, it's only able to crack the rock. And then it comes and hits the surface, gets reflected, can form a crater, rock gets thrown out to create cracks growing down, as some of you might have seen the Pokhran craters would have done. We had predicted all this. Our main reason was that we ensure that there is no venting of radioactivity in any of these devices. That's why, in fact, we have to contain the radioactivity. 45 kiloton, by changing the isotope composition, controlling it is more difficult than raising it to 200 kiloton. So, this is the test 5S. What you see here on the left is the big one, the thermonuclear device, and is the advanced fission device. Then we tested what I call them 3 chotus, less than 1 kiloton. In order to renew, this is the only chance for testing we are going to get. So we tested out a large number of physics principles so that we can now modify the device the way that we want. And much of this is given in the article which I mentioned. Next slide. You know, historically, nuclear weapons knowledge has been shared among countries. After our test, this guy, Payne and Mackenzie, they wrote a paper in which, because UK and US were partners in their test. US to Russia came by leakage. US to France because they were friends. Similarly, France to Israel, Israel to South Africa. Russia gave the information to China. China gave it to Pakistan. But they realized that India neither spied nor took the knowledge from anybody because it did not have to. We had all the knowledge that we needed to test, to design and test all the devices that we needed for India's nuclear deterrence. Next slide. So in the 10th NIDOMA lecture, which was given in Tenali in 1999, I said national development and national security are 2 sides of the same coin. Development without security is vulnerable. And there are examples of that. Look at Japan, so well developed, but they are afraid of a small country like North Korea because they have nuclear weapons. Security without development is meaningless. That's what Russia, Soviet Union realized. Nuclear weapons, they were on par with the United States. But then they realized that's not enough. And then Perestroika, they went in for development. And I've said in this talk, the greatest advantage of recognized strength, whether it's a human being or whether it's a nation, is that you don't have to use it. The greatest advantage of perceived weakness is that your enemy may get adventurous. As I said, this is the principle behind nuclear deterrence. Next slide. See, of course, today no country can be isolated in science. You need cooperation. No country can build some other facilities like the Large Hadron Collider. So in Geneva, so as you know, Einstein equation E is equal to mc squared. And fission takes place, the resultant product has less mass than the mass of the neutron and uranium 235. Let's say that's the one that underwent fission. The difference in mass, reduced mass multiplied by c squared gives you the energy. E is equal to mc squared. Similarly, when particles collide, energy disappears. So Einstein equation you have to read backwards. Energy disappears, mass has to be produced, provided the energy is large enough. And that's how they created this Large Hadron Collider. It's 126 kilometers underground in Geneva. In fact, all the superconducting magnets for the protons to go around were supplied by India. Maybe $20 million, $40 million worth of equipment. Actually, we spent 20, but 40 million is estimated at European cost. All the 180, 86 sextupole, octupole, decapole. See, dipole magnet bends the charged particle proton, but focused by these sextupole, octupole, and decapole magnets. And our people also participated in this detector. KFR was a detector, same as we saw the Higgs boson, which for some strange reason was called the God particle by some people, not all. Similarly, in the ITER, International Thermonuclear Experimental Reactor in Kadarash, where they are building a thermonuclear experimental reactor, India has contributed. One of the major contributions is this cryostat, in which the whole tokamak is housed. Largest tokamak in the world, the largest cryostat in the world, 30 meters in diameter and 30 meters in height. That was supplied by the Institute of Plasma Research in Gandhinagar, which is one of the institutes under the Department of Atomic Energy. Next one. This is the cryostat designed by IPR and made by L&T. Is either installed now. Next slide. See, that was one area which we have not done very well, hardware electronics. In fact, say 20 years back, we were leaders in software, but nowhere in electronics hardware. Systems, we were very good, but in components, when I mentioned it to the minister, Arun Shauri, he said, I'll give you 100 crores. I said, we must set up centers for nanoelectronics. So these two centers were set up, IIT Bombay and Institute of Science, Bangalore. They have state-of-the-art facilities, very active. And of course, they have improved. Many other places have also come up. So many startups, you can see that thing here, training programs. So many companies are using it. Look at the productivity from these two centers. And we also created, since it was a very large outlay, so we said you must also have an Indian National Users Program in nanoelectronics. And this is now, and which was funded for scientists to come and work there. This slightly couple of years old slide, but then already 700 institutions and more than 7,000 researchers have used this. Next slide. And then this was the other thing, from our PSA's office, we got it approved by the Prime Minister's office that whereas the US had networks like Internet 2 and in France, India didn't have a optical fiber network. So this was allowed. So we got quite a bit of money, 1,500 crores. And this is how this was built up, National Knowledge Network. Of course, they're done by MITI, the Ministry of Electronics and Information Technology. And very large number of institutions. You can see that maybe now it has risen to 2,000 knowledge institutions in the country are all connected. And this is this very interesting book, Noah Harari, Homo Deus. First he wrote the book Homo Sapiens. This is Brief History of Tomorrow. And I quote, humans nowadays completely dominate the planet. Not because the individual human is far smarter and more nimble-fingered than the individual chimp or wolf, but because Homo sapiens is the only species on Earth capable of cooperating flexibly in large numbers. And communication, the foundation on which cooperation is based. Started with language, continued with telephone, and then now of course, we have this optical fiber communication, networks, and then, of course, we also need these supercomputers, Anubhav supercomputers, and this is India has now supercomputing mission, but most of those are imported. But multi-petaflop machines built only by PARC, partly because nobody will supply supercomputer to BRC. In fact, it was started during my time, and computer division was part of the physics group. Now they are world leaders in designing parallel processing supercomputers, and that's what you see here. So I thought what I will do, go ahead. I think I will see now the talk is on artificial intelligence. Artificial intelligence is omnipresent. Of course, we are using it also. Robots are there, AI robots, and you can create expert systems. Many years back, we created. See, after the 2015 flooding in Chennai, which should not have really happened, we decided we should go in for an expert system based on artificial intelligence. And now they have spread all over. How much to nuclear power? Our nuclear power corporation also uses artificial intelligence based expert systems for error diagnosis, where action should be taken. Of course, the final right to take action is only with the computer is not allowed to take action. Like in medical ethics, you can use artificial intelligence, but the decision cannot be taken by the machine. It has to be taken by the doctor. But there are some people who are scared of the long-term developments, including the great astrophysicist Professor Stephen Hawking. He told a BBC correspondent some years back, the development of full artificial intelligence would spell the end of the human race. I don't agree. I agree more with people like the mathematician Roger Penrose and some other leading scientists who argue that application of Gödel's incompleteness theorems, 1931, very interesting theorems. See, what the theorems say is that, when you form any theory, what do? You set up a set of axioms. All you can say, none of my observations so far are inconsistent with these axioms. Mathematically, you cannot prove the theorems unless you go outside the system. And you cannot go outside the system. That is the theorem Gödel's incomplete Roger Penrose uses to conclude that humans will always be smarter than computers and computer algorithms and any other cybernetic machines that they create. I fully agree. It's a very interesting book by Howard Gardner, old book, talks about the theory of multiple intelligences. Says intelligences have many dimensions: musical, linguistic, visual spatial, bodily kinesthetic, logical mathematical, intrapersonal, then he added naturalistic, and spiritual existential. How many of these can be artificial intelligence? I ask myself the question, and my conclusion is only the linguistic, visual, spatial, logical, mathematical, anything creative, very good. Maybe one day it may, but that's a debatable point. So, I think you don't have to have the worry that Stephen Hawking had. We agree more with Roger Penrose, at least I agree, that no computer algorithm or any other cybernetic machine can ever overcome the human race. Then, question of cybersecurity. One of the other major issues nowadays, we try to protect all our you protect whatever anything you put on the network, you have to protect cybersecurity. But then the hackers are also intruders. Attackers are also getting smarter. Apart from the common types of cyber attack which I mentioned here, or Internet of Things based attack. Once you connect, you are vulnerable. The greater security is in isolation, but you cannot isolate yourself. And the attackers are also beginning to use artificial intelligence and machine learning for new kinds of attacks. Now this has been examined. For example, McAfee Threat Predictions Report. First major supply chain attack which took place in, he calls in US. December 20, by disrupting the supply chain, you completely disrupt supply of materials. And the cybersecurity experts called it a cyber Pearl Harbor. But there are many academic institutions in India working in the SETS, which we had Korea organization by the PSA's office. Then we have a National Critical Information Infrastructure Protection Center, Critical Information Infrastructure. SETS, this is the one which I form under the PSA. It's working in frontline fields like AI, machine learning, blockchain, quantum cryptography, communication. If and when the quantum computer comes, maybe not for a decade, it can break any RSA code created by a classical computer. Now, one talks about post-quantum cryptography. And all these, you had a report also by Professor Raman, IIT Madras. See, if we look at this, research, development, delivery. In the case of rural development, the problem is with delivery. Development also is a problem. And we had started this Rural Technology Action Group in 7 IITs. And it's an open platform innovation strategy. A lot of work has been done in these seven IITs. And sometimes, you know, smokeless chula, for instance. Smokeless chula is a very good innovation. But the way a South Indian woman cooks is different from a way a UP woman cooks. So, but the principle is the same. So I had used this concept of what I call re-innovation, followed by concept transfer, followed by re-innovation. But you know, this it can make a lot of difference. I've noted that a person near the poverty line, her quality of life is a very non-linear function of the income. Look at a potter. IIT Kharagpur had done a wonderful work. Why do they use the hand when a sewing machine uses the foot? So they designed a pottery machine operated by the foot. You want only a rotary motion, and both hands are free. So they are able to make design much better pottery using rotation created by the foot. Of course, if you put a motor, you'll be one. even better. And if you do a thing like that, productivity goes up. And as I said, suppose a person earns 100 rupees, 90 rupees goes on survival. His quality of life is proportional to 10 rupees. Suppose I double his income, his quality of life goes up by an order of magnitude. Suppose I double my income, or Dr. Keshavda's income, Dr. Ishwar's income, only our bank balances will go up. Our quality of life will not go up. Next slide. And you know, we can, rural technology, we have done all this. There was a ravine here. It's a natural ravine. Because I got interested in this after this big flooding that took place in 2015. Poor ladies used to go down. These are natural ravines. Come up on the other side, carrying the produce. Lions are on one side and they live on the other side. The least thing that can happen to them is they can sprain their ankle. So we built this bridge, and I called it, because once I saw a DRDO building bridges for the army to go when you are going into enemy territory and they find a ravine like this. I requested them to design it for rural. This is in Uttarakhand. And so successful it has spread in all the hilly area, Uttarakhand, Himachal, and so on. Next slide. See, let me come more or less to the end. India for dreams. Hello, young people in the audience. India for dreams is an India which is economically developed, but the human development index is high. An India which is scientifically advanced with a knowledge economy, the research development, innovation ecosystem with excellence in basic research. You can't build a technology superstructure without a foundation of basic research. But you can do what I call directed basic research, not applied research. Basic research directed towards India's needs in the long term. And all this has to be backed by high quality manufacturing skills. Of course, we also want an India which is militarily strong. You know, India is a very unique country, economically developing, where parts of the S&T system are very highly developed. We also need to increase our appetite for risk-taking. Phil Rosenweis in his book, This Idea is Brilliant, edited by John Brockman, says, when it comes to technology breakthroughs or launching new products, it's better to act and fail than fail to act. And our Nobel laureate, Indian Nobel laureate Abhijit Banerjee, I was listening to a lecture by him. One slide was risk and poverty trap. And he says, poor people take up low risk, low return projects because they fear the risk. So they remain poor. Same thing is true for research. If you take up low risk research projects, you'll do good work. But if you take risky research projects, then you can do great research. And I said before, the so-called proven technologies, unless subjected to continuous evolutionary improvements, are only a synonym for obsolete technology. Thank you very much. I think I'll close.
Sir, thank you very much, sir, for inspiring us with your experience. It is amazing to understand the road that India has traveled since independence. There are a lot of young scientists in our midst with a lot of questions. The first question is from Dr. Arvind Prajapati from the Biomedical Technology Wing.
Yes.
He's asking whether there are any common traits, behavioral traits of these renowned personalities such as C.V. Raman, Homi Bhabha, which could be pursued by the young scientist in the early stage of his career.
Very difficult to say. Of course, they are all intelligent, but the intelligence is not enough. You need creativity. And creativity is an elusive thing. And it is very important. You know, I started a program for gifted children. A bright child is not the same as gifted child. A bright child can understand whatever you tell, but a gifted child thinks different. So it's actually, most of these discoveries are made by teachers when they have young people under them. Suppose somebody says, I remember when I was discussing this with my American colleague, he gave an example. American teacher teaching lower KG. He was telling them 7 is a larger number than 5. 7 is bigger than 5, 5 is smaller than 7. You can subtract 5 from 7, and 7 you cannot subtract from 5. So this 3-year-old piped up and said, what is the problem? Answer is -2. No, the teacher was trying to tell numbers. From that time, the teacher became hostile. And the child's mother had to go and talk to the teacher. Even when we teach, you must always concede somebody in the audience who is smarter than you. They may know more in an area. Of course, they know in all the areas you are talking about, better he give the lecture and you go to the audience. But I'm saying in selected areas, you'll always find then you have creativity. That's the only great thing about not intelligence alone. Of course, you need intelligence, but not enough.
Thank you, sir. Thank you, sir. We move on to the next question. This is from me.
Yeah.
The director of the IIT, the former director of the IIT Madras, Dr. Anand, had this anecdote from his experience. When the IIT Kharagpur was inaugurated by none less than Mr. Jawaharlal Nehru, the first Prime Minister of our country, he made a remark that these are temples of temples of human progress in our country, and they will stand to serve the nation. But what Pandit Jawaharlal Nehru forgot to tell was which nation that these temples of progress will serve. All the IITians aspire to go abroad just as anyone else. How do we stop this brain drain from hitting our Indian science?
I've not gone abroad, but I'm also not from IIT. I'm more from Indian Institute of Science. See, there are plenty of people. See, there's nothing wrong in going abroad after your master's degree. But I want them to come back after the PhD. And now, I looked at it when I was the PSA. More and more people are now wanting to come back to India. As India progresses further and further, you will find, and this year, whatever you say, the quality of life in India for Indians is much better. See, why do you get service like you get in India? Do the women, the wives, do they have a servant there? You can't afford it. Here, of course, it may not last till the next century. There's a different issue when the lack of quality of life. But then, how much can a gadget do? A human is, after all, a human. So my feeling is they will come back. And second thing we realize, that India has a surfeit of intelligent people. There are enough intelligent people in India to take forward, even if they don't come. India is not dependent on importing intelligent people. That's my view.
Thank you, sir. The next question, of course, is from Dr. Kamlesh Gulia. What is your dream of India in nuclear energy capabilities in the next 25 years?
See, nuclear energy is going to become more and more important because you will find that burning coal and creating too much of greenhouse gases is going to create a problem. This problem is going to get worse. You have to cut down on burning fossil fuel. Hydroelectric is very important, very safe, but then as the population of India increases, building hydroelectric dams, big dams, by displacing people is now practically impossible. Though you can build mini and micro hydel plants. Renewable energy is going to be extremely important for India, particularly solar energy. But solar energy is intermittent. What do you do when the sun is not there? Now you have to store it. Where do you store it? Lithium-ion batteries? How do you produce the lithium? These are all going to put limitations. As you go on, as it is in my own opinion, that nuclear energy will become more and more important. Because you plot the Human Development Index, which I have done 30 years back. Per capita electricity consumption monotonically increases. Human Development Index is defined by United Nations in terms of 3 parameters. Per capita GDP, life expectancy at birth, adult literacy. I've said you only need 2 parameters, per capita electricity consumption and female literacy. I prefer female literacy to adult literacy because the female literacy is a measure not only of literacy but equity and justice in that society. In Kerala, hardly any difference between male and female literacy. But even now, if you go to eastern UP, parts of Odisha, the lower the average literacy, the greater is the difference between male and female literacy. That's a different point. But per capita electricity consumption. Per capita electricity consumption has to increase by 6 to 8 times. Because otherwise, how do you get industrial production? You have to increase industrial production. But at the same time, you have to prevent the climate change threat. That's how you will find that nuclear energy's importance, in my opinion, will continue to increase.
A connected question. So, thank you for that excellent talk. The nation has built a lot of national institutes, and like All India Institute of Medical Science, 10 or 12 of them, and a lot of research institutions. But all of these institutions are significantly underfunded. I mean, and that underfunding seems to be having a problem with doing significant amount of research activity. Now, is this a matter of misplaced priorities or lack of foresight? I mean, why do we build institutions and underfund them? Since you have been the president and we know that we have had a wonderful time with you, sir. So how would we address this problem?
Tell me one institution is overfunded.
They're not overfunded. I am asking underfunded, sir.
No. In others, we are talking about medical institutions. Every institution, they'll mange more money. So we have to go and fight for it. Because after all, there is a budget. There is the gross national product. You can increase the percentage of that thing. I agree with you. The percentage of money, you must increase part of the GNP. They are much lower than China. That must increase. And it is increasing, but not as fast, slowly increasing. But then you have to find priorities here. I would like all institutions to be funded better. More than that, very important that all important projects are funded. See, science is done by scientists. And it is done through projects. Good projects should never be underfunded. That's my feeling. But money is a problem. I agree with you that there's no other way. Everybody wants more money. We want more money for roads. We want more money for other things. You want more money from healthcare? Yeah.
Thank you, sir. I think we have the head of the biomedical technology wing, Dr. Harikrishna Verma, waiting to shoot a question to you. Over to you, sir.
Don't shoot me. Shoot the question. Okay. Yes.
Sir, you're muted.
Yeah, 1 minute. Sorry. Sir, excellent. It was a great opportunity to see you again and listen to you, sir. So my question is that one, BARC and we have a DRDO, we have excellent quality super alloys and many metallurgical innovations has happened. But when I approached Midani for even titanium, for an industrial use or the technology which we develop, we still don't have any such quality materials for medical grade. How we circumvent this one, sir? Because we can develop technologies, but when we approach the raw materials, we still don't have supply. So how we do this?
See, this requires interdisciplinary research. You have a demand, they have the knowledge. So it is happening, beginning to happen now. For instance, if you can have a funding agency or you can combine it between you get money from the medical funding agencies, they get the money from, say, Midani, from CSIR. Together you can propose a joint project. They won't mind that. See, the problem is they have asked for some money with a very focused program. Unless it fits in with them, with their program. So it has to be planned. It requires, not easy, but it has to be done. And that habit has not yet come. Multiple agencies funding interdisciplinary programs in different institutions and institutions collaborating with one another. But the next best thing you can do is to search out those, let them do what they want. You'll be very happy. As long as they don't have to part money for you. They'd be willing to develop the material because it's good for them, for the material side guys. And they'll develop with very little additional, that extra bit of extra money can come from your budget. Probably that's the way it will go, because all over, the only thing that's going to happen is interdisciplinary research. Single discipline research is slowly all over. Everything is now multidisciplinary. And either it takes some time for the funding agencies to do that. But we ourselves can do it. You have the money, they have the money. Together you have a joint project. You can propose a joint project. They're getting the money from somewhere, you get the money from. Or from your own parent institution.
Thank you again, sir. I think we are behind the schedule, but we still have a lot of questions on the question chat.
I'm free. You people may be busy. I'm free till
Sir,
go
there's
ahead.
one question from our scientist, Dr. Jayasree. With high demand to reduce carbon emission and use of fossil fuel, what is your opinion on relying on nuclear power and the sustainable production, especially in view of huge investment and non-equitable power output?
Don, what's the last one?
In view of the huge investment and non-equitable power output.
What is a non-equitable power output?
I think what she means is different states do not get the same share of power. I think I don't think that happens in India.
That goes into a grid. You don't even know where the power is coming from.
Okay. All right. Now, what about the replacement of carbon emission and fossil fuels by nuclear power in the days to come?
You have to come over a period of time because we are going to be burning coal for a long time. Because you remember, it's not just power is not the only parameter for development. There are coal mines, there are coal workers, there are transportation of coal, people involved in that. It's just not physically possible to do a delta function change. It has to be preferably a second order transition. Nobody feels anything is happening. But it is going to come. As our coal supplies dwindle, cost of transportation goes up. You see, cost of transportation of coal is much, much higher than cost of transportation of nuclear fuel. Remember, electron volt versus a million electron volt. What is the difference? Amount of quantity of fuel when you are talking about. These transitions will take place, but over a period of time, and renewable energy will come with storage, but then up to a point that will work, or at least various points without need for transmission, distributed renewable. But then storage will continue to be beyond a point. But basic load has to come, basic power has to come from hydro, nuclear, and coal.
Thank you, sir. We have another question from an engineer. So Sharath S. Nair wants to know whether nuclear batteries will, as storage medium, will substitute lithium-ion batteries in implantable medical devices as well as electric vehicles in the future.
I personally don't think so. Because the demand is so high. For a pacemaker, I can give you a plutonium isotope. Use the heat, thermoelectric power, then you can get a pacemaker. All the pacemakers have a radioisotope, by the way. You know that. But you cannot supply from there. You have to supply power from outside. But that kind of thing very unlikely. Lithium-ion batteries, maybe sodium-ion battery. A lot of work is going on sodium-ion batteries. Because lithium is a somewhat rare metal. Not available everywhere, actually in China maybe. Sodium-ion batteries, a lot of work is going on, but not yet economical. But it will come. Sodium-ion batteries will come. Then it will become. Sodium is plentiful.
There's a question from Dr. Biju Soman, from the Public Health Division of our institution. How can we harness the advantages of artificial intelligence without infringing on individual rights and moral codes? More of an ethical question.
I don't think there is any individual. AI has now application. Whether you like it or not, it's all over the place. Whether you like it or not. It doesn't infringe on human rights. Tell me one technology which you can misuse to infringe human rights. I can always devise a method of doing bad to humans. But this one, artificial intelligence has applications all over the place, applied everywhere. Why can't I use artificial intelligence flood forecasting? Why should floods happen in Chennai? If I can get a prediction 24 hours in advance, use artificial intelligence. You can at least evacuate the people, and that information you can get at the ward level to remove it. Artificial intelligence in diagnostics, medical diagnostics. So the final decision is made by the doctor. Of course, robotics is part of artificial intelligence. Robotic surgery, but the control is with the doctor. Doctor has the final control. Anything related to artificial intelligence in medicine. Yes, please go ahead.
Sir, sir, I'm Biju. Sir, I was a bit concerned with whenever we totally depend upon artificial intelligence for decision making. For example, like the self-driving car. If we leave it to the coders to decide upon what should be the right and wrong, then and we blindly follow that, then we might end up in trouble. So that's why I think that as health professionals, we also should have some idea about how it works, and we should get to know about how the sort of data management occurs and how decisions are made. And in the coding process, in the preparative phase also, we have to bring in this sort of domain expertise, be it public health or clinical medicine. So that was my point, sir.
See, automatic driving, I don't believe in. Even Elon Musk doesn't believe in that. A human, when he drives, so can you program a machine to all kinds of emergencies, in the case to avoid a collision. But if a new situation arises, somehow a human reacts in a proper way. A machine, unless it has been taught, it cannot. It is not able to react. Everything has to be taught. That is, what was the second part? I was concentrating on this automatic driving. I don't believe it will come. Yes.
Yes, sir. For example, when we are looking at a pandemic situation like COVID,
Yes.
looking at various data from Google Mobility and all, if you decide upon going for lockdown, would definitely control the epidemic and all. But that alone actually be in what all ways it can affect the common lay people in the community. Actually, that also should be taken into account.
It's entirely up to you. See, you must have all the data. Any decision you take, whether it is based on artificial intelligence or normal intelligence, you have to analyze the consequences. Surely it applies to artificial intelligence. You can't limit it to one decision. What happens as a result of it? You have to look at it. There is no, you are absolutely right. There is no question about it.
Thank you, sir.
If you can, of course, humans can always make a mistake. Then you correct, like humans do. AI systems can also be self-corrective. You can teach it not to make the same mistake again. Because serious mistakes, that's a different thing. But then humans also make serious. Humans driving, you have an accident. What happened? Your attention goes somewhere. Talking to your friend, and you don't see the car coming. Or you have a faulty tire. So same things will happen with, but some of those situations, you can't give the full control to the artificial AI. For example, if you are handling radioactive material, you're handling hazardous material, already robotics is being used. Robotics, because you don't want humans to get hurt in case something goes wrong. And robotics is a part of artificial intelligence. It's already happening. Hazardous materials and these kind of things. Or you want to go with earthquake has taken place. You want to navigate a vehicle into dangerous areas. Then you can use an autonomous vehicle, control it. Because you don't want a human to get injured. Whatever happens to the vehicle, you don't care. So we have to look at the situation in which you are using an AI system.
Thank you.
Thank you, sir. I think we need to wind up. We have a couple of more questions. This is a Kerala-specific question. We are rich with the thorium deposits in our beaches. Is there any hope in using thorium as a primary fuel for running our nuclear power?
This is the basis of our good question of our three-stage program, because we have limited resources of uranium. What we have done is to build reactors which use natural uranium, pressurized heavy water reactors, because they are good at converting uranium-238 to plutonium-239, which is a fissile material. Second stage is to build fast reactors with plutonium-239, like the one that is coming up in the breeder reactor in Kalpakkam. There, you expose thorium to it. In those reactors, the cross sections are better. Thorium-232 gets converted to uranium-233. And uranium-233 is a very good fissile material. So in the third stage, not thorium, but uranium-233, to which it has been converted, will be the mainstay of our program. That's some decades from now.
Thank you, sir. And the last question, as we have already shot past the time that we have allotted for this lecture, how about disposing nuclear waste? Are they going to pose a threat to the environment as well as the human existence?
I would be more worried about biological waste. Nuclear, we have very, very careful. See what we do, high-level waste, we convert it into vitreous waste. Vitreous waste is waste in which even if water comes, nothing will leach out of it. Then we bury it underground in places where there's no water. And because the amount of waste is much less compared to the kind of waste we talk about. What about fly ash, for instance? That comes with coal, huge amounts of fly ash. Affects your respiratory organs. We put back, convert it into bricks. Of course, people are looking at methods for everything, and we have solutions for taking care of radioactive waste. I don't think it's going to pose any problem, provided we handle it properly. Because you must know, when we have all the capability. As I said in the beginning, India is one of the few countries in the world which has got all capabilities, starting from mining to radioactive waste management.
Thank you, sir. I think we need to pull the curtains down on this lecture because we have passed our scheduled time. Thank you, sir, for your patience and also the audience for all the questions that has been raised in this forum. I invite Dr. Kamlesh Gulia, who had actually done everything possible to make this lecture happen, to render the vote of thanks.
Good evening, everyone. I, Kamlesh K. Gulia, I'm greatly honored and privileged to give the vote of thanks today. Through Samvaad, the international lecture series by the SCTIMST, at a time when we are celebrating 75 years of our independence as Azadi Ka Amrit Mahotsav, listening to our former president, Honorable Dr. R. Chidambaram sir, the noble think tank of India, has been a dream come true for us, sir. Each word of yours was golden and inspiring. Your thoughts laden with the national pride, indeed, took us to a special ride of the pride historical moments of achievements from Pokhran to the current know-how of the Indian journey of science and technology. Honorable sir, I am emotionally speechless. With great honor, I feel that the words are too less to express our gratitude to you. We are so thankful to you for giving such a spectacular, glorious, and magnificent account of the Indian science and technology, and also at the same time giving us the future directions on AI, super intelligent robotics, medical devices, step for green India, and new low carbon technologies, electronics, need for NKN, supercomputers, etc., etc. All these which will help us in making a roadmap for a single aim of raising the Indian flag higher and higher in the global space. Thank you very much, sir, for giving us an outstanding opportunity to listen to you. I'm delighted to express my deep gratitude to our dynamic and energetic director, Dr. Sanjay Bihari, sir, who gave us this superb idea of initiating the international lecture series, Samvaad, which is becoming popular now. Thank you, sir, for your endless support at every minute, every hour, each day. I express my sincere thanks to our beloved Deputy Director, Dr. Keshav Das, for wonderfully conducting the QA session with Dr. Ishwar. Thank you, sir. And Dr. Ajit sir, please get well soon. You are having some infection. I'm thankful to Dr. Ishwar for introducing the speaker today, and also Dr. Keshav Das, and for rendering all possible help behind the scene. I thank our computer division, including engineer Suresh and the team, for creating platform for the lecture and its live streaming through YouTube. Last but not the least, I express my heartfelt thanks to Dr. Rupa, Medical Superintendent, Dr. Verma, Head Biomedical Technology Wing, all the admired participants who joined today's lecture and make it such a successful event. Thank you, all of you. Also, we, the Chitra fraternity, are eagerly looking forward to physical meeting with you, sir, Honorable Chidambaram, sir, in the near future in the SCT. We are looking forward to an opportunity. With these few words, on behalf of our mini Samvaad team, including Dr. Mala and Dr. Ishwar, I once again express my sincerest thanks and gratitude to each and everyone who is connected for the Samvaad lecture and all those who have helped directly or indirectly in this endeavor. Jai Hind, sir. Jai Hind, everyone.
And thank you very much. I'm also looking forward to my visit for your meeting on epilepsy, where of course your institute has such a great expertise from the time to Dr. Radhakrishnan and Asha Lata. Where is Asha Lata? Is she around? No. She's arranging this meeting, this conference, no? Yes. On epilepsy. On epilepsy. Asha Kishore was there after. Of course, Dr. Valiatan was my old friend for a long time. Thank you very much. Looking forward to my visit to your institute.
Thank you, sir, and have a nice evening.